Good morning, my dear students. Good morning. Nice to meet you all. Okay, very good. Nice. Good morning to all of you. Right. For today's discussion, just 1 minute. I will project the notes. Okay, we will see. Last class, I told you about how to develop a shape function for uh, actually 8-noded rectangular elements, isn't it? So when you discuss this kind of plane element, 8-noded rectangular elements, nonlinear element, I told you to consider a line element here. Okay, line element to represent this R, it is RS system. For R coordinates, you have to draw a line element here. Okay, you have to name the nodes as 1, 2, and 3, right? Irrespective of the names, nodal names here, right? And then to represent the S direction, you have to write another line element, and you have to represent its node as 1, 2, sorry, this is 1, end 2, here 3, right? Middle 3. Its values also, the natural coordinate varies from here -1 to +1, here -1 to +1. After writing this, you have to write the coordinates for this nodes, okay? Because here here -1 is there, here also -1. That's why coordinate of this node is -1, -1. If you come to 2, here +1 is there, here -1 is there. That's why 1, -1. Like that, you have to do it, right? And then you have to write the shape function for this line element, the direction, R and S direction. Okay, for which you have to write this one. Which one? Shape function. Already we have seen for the line element, the one-dimensional line element, the shape function is nothing but the Lagrangian polynomial. We have seen already. Okay, that is why I am writing the shape function for the line element for node 1, node 2, node 3 as L1R, L2R, L3R. Okay, straight away I am writing the Lagrangian polynomials. Okay, which are nothing but a shape function for this one-dimensional line element that is representing the R and S direction. Okay, likewise we have written its variation also shown, right? Already you have aware of it. Accordingly, since it's a nonlinear, variation is nonlinear here. Okay, it's shown because every shape function has got a unit value in its own node and 0 values at other nodes. This is the law. Okay, likewise we have drawn. In order to get a shape function for this rectangular element, what we have done, we followed the superposing technique. Okay, superposing these, they are called fundamental polynomials. Okay, this shape function for this one-dimensional line element, which is nothing but R and S direction. Okay, which are called fundamental polynomials. By superposing them, we can obtain the shape function for 1, 2, 3. Right? This and all I showed you how to superimpose. I told you, for suppose for node 1, N1 you want to write. Come here the unit value is there. So therefore L1R. From node 1, go in horizontal direction. Here unit value is there. So therefore L1S. Likewise, you have to multiply these two. Okay, this way superposing is done. Thus, we obtained the shape function for the rectangular elements, all the 8 nodes. Okay, and if you substitute the fundamental polygon value, fundamental polynomial values, fundamental polynomial is nothing but the shape function of that one-dimensional line element, that R and S direction, that line element we are taking, the directions as line element, for which we obtain first shape function. We call it as fundamental polynomials. That by superposing techniques we are substituting here so as to develop the shape function for each nodes. Okay, this way. This and all we have seen in detail. Okay, today I am going to tell you about Lagrangian rectangular element. Right? This is ordinary 4-nodal rectangular element, 9-nodal rectangular element we have seen. Okay, today we are going to see Lagrangian rectangular element. What is the Lagrangian element? Please recall. Lagrangian element is nothing but in addition to this edge node, okay, corner and edge nodes, it has interior nodes in line with edge nodes. Okay, we call it as a Lagrangian rectangular element. That's all. For a 9-noded Lagrangian rectangular element, and the fundamental polynomials can be written in both on the R and S direction as shown. Okay, that's what as shown in the figure. Its variation can be shown. Same figure, the same figure, the same thing only. Its figure, the figure is here, clear here. Okay, the same figure only I have drawn. Okay. Only exemption is here we have a node at center. Okay, that's all. all other procedure are 100% same that of this rectangular element, except we are going to develop one more N9 here. All other things are same. For Lagrangian element, you have to write N1, N2, N3 up to this right, okay, up to N8, the same procedure. For Lagrangian element, whatever you have done in the previous discussion, 8-nodal rectangular element, same thing as it is, ditto, you do it, okay. Afterwards, the only addition is N9 here, okay. So that's what. See here, the Lagrangian element is shown, it has got interior node in line with edge node, okay. In line with the edge node, it has got interior node, okay. We call it as a Lagrangian element. So this figure I have not drawn properly. Here you have to draw this line element, the one-dimensional line element you have to draw here, okay, and represent this node is 1, this node is 2, this node is 3. Here this one varies, natural coordinates varies from -1 to +1, and also here you have to draw the line element and say this is first node 1, node 2, middle is node 3, and here you have to represent the natural coordinates varies from -1 to +1 as shown here. As shown in this figure, you have to draw the same manner. Here I have shown the same manner you have to draw. Okay, they are missing. So roughly drawn this sketch. Okay, because already we have discussed. That's why roughly it's drawn, right? Then by superposing, the shape functions can be written as follows. Okay, already we have seen how to write similar to that of 9-noded, 8-noded line element. Previous the one. Now the only addition here is N9 up to N8. 100% similar to that of previous discussion. You have to write as it is. Okay. Now N9 is equal to how L3R and L3S go to the figure. Okay. Here this 9th node come down. From 9th node come down. Which one has got unit value? L3R. Okay. From 9th element go there. Which one has got unit value? L3S. That's why L3R into L3S. The N9 equal to. Okay. Now, up to N8, same, all already obtained. Okay, the previous discussion already we obtained up to N8. N9 is the only addition. You know the fundamental polynomial, substitute here, you will be getting this one. Because in a very brief manner, I have written my notes. Okay, but in the class, I used to write everything. Please, I advise you, prepare your notes accordingly. Already, you have developed, substitute them and do it. Okay. The development of shape function for the quadrilateral element will be explained later under the heading isoparametric elements. Okay, very good. See, sir, what about the development of shape function for quadrilateral element, isoparametric element? I am going to discuss. Small discussion I am going to do. I am going to tell you what is isoparametric element, what is sub isoparametric element, what is super isoparametric element, sorry, what is isoparametric element, what is subparametric element, what is superparametric elements. I am going to explain. This discussion is important. And then if any quadrilateral element is given, that is converted into parent element. Okay, the quadrilateral element will be taken converted into element called parent element. That will be the isoparametric element. Okay, for the conversion we are using a matrix called a Jacobian matrix. Sometimes you will be asked what is Jacobian matrix and all. This much discussion I think more than sufficient. If I want to discuss about the properties of elements, I can keep on discussing. That much is there. But already we have discussed enough. No teacher will discuss this much who teaches finite element method. Okay, already I have discussed a lot about properties of elements with you. I think this much is sufficient. Okay, but another one important element. 1 minute. I want to have some water. Okay, 1 minute. 1 minute. Okay, no problem. Camera on, no problem. Okay, what is it I was telling? Yeah, actually, yeah, this one, this discussion we are going to on another important element I have not told you, that is a two-dimensional beam element. Okay, how to develop a shape function for two-dimensional beam element, that entirely differ. So far we have seen one-dimensional line element, we call it as axial element, that is one-dimensional. If the same line element is kept in a plane, we call it as truss element, two-dimensional line element, that is a truss element. Okay, either it may be one-dimensional, the axis may lie with the element itself, or the axis may be somewhere, the element will be lying somewhere arbitrarily. Okay, two-dimensional. Even the same line element is put in space, three-dimensional line element, like that one-dimensional line element, two-dimensional line element, three-dimensional element, we can say, okay, they are truss element, okay, it can be kept anywhere. And then mainly in two-dimensional element, we have seen all plane element, okay. The most widely used plane elements are triangular element, rectangular element. Both I have discussed with you in detail, right? And then another important element that also most widely used, that is beam element, okay, which is also like line element, but two-dimensional. We are taking the degrees of freedom as not only the translation, displacement in along the axis, rotation, okay. That is why it is two-dimensional. That way it become two-dimensional. Okay, that I am going to discuss the development of shape function for it in detail while teaching you development of element stiffness matrix. There I am going to discuss with you completely. One beam element will be taking, because beam element is very important for us. Okay, first we will develop a shape function. That we will develop a strain displacement matrix. Then we will be developing element stiffness matrix for it. That discussion I will do it afterwards. Okay, not in the second unit. The third unit I am going to discuss. But keep it in mind, the development of shape function for two-dimensional beam element is missing here. That I will be discussing in detail while discussing how to develop element stiffness matrix for a together. I want to discuss that, then only will understand, follow. Okay, that also may lie in the second unit. Development of shape function for two-dimensional line element lies into second unit. It will be discussed in the third unit with the, okay. That's what is written here. Shape function for solid element, tetrahedral element, hexahedral elements, not there in your syllabus. Okay, it is not there. Three-dimensional element, the solid element and all, not, we will not go too much into the detail. For this itself, you feel hard, no? So we need not go too much into that. That the software will take care of. See, all of you listen. We have been discussing all these things. While using the package, do you think that you will get the elements with the same name? No. The element will be with a different name. Okay. For example, the one-dimensional line element, it is called link element there. Okay, link, some number will be there. Link its property, accordingly it is assigned in the library, the package. Those elements are available. For example, for concrete, okay, your material is concrete. You want to discretize that continuum, the concrete beam. It's a continuum. You want to discretize it. There you will be using while using solid 65 element. Solid 65, some number is there. Similarly, to represent the FRP wrapping, some shell element. Okay, I've forgotten the names of those one. Okay, because I have used widely long back this wrapping, FRP wrapping. For that, there is a latest 188 something. Shell 188 something, that I forgot that name. Okay, those elements are called, the library, the elements names are called like that. Although you study this way, triangular element, rectangular element, 8 noded, 3 noded, you are studying there. You will be in the package, you will be calling it with a different name. That also you keep it in mind. So you must be familiar of which element to be used for. Just now I told you, for concrete, solid 65 element to represent the reinforcement in your concrete you are placing. No, there you have to use link element in the package. Okay, let us see. We will discuss further. Now I am coming to isoparametric elements. Sir, what is isoparametric elements? Isoparametric elements, now please all of you listen. You, for example, you take a triangular element, right? The nodes, you have 3 nodes, no? Say the displacement at node 1 is U1, V1. Because two-dimensional, we are resolving the displacement is some direction, its rectangular component is taken. Okay, node 2, you have U2, V2 displacement. At node 3, you have U3, V3. They are the nodal degrees of freedom, nodal displacements. Okay, now you take the coordinates. Okay, geometry, that's called geometry, coordinates of node 1, x1, y1, node 2, x2, y2. In the Cartesian coordinate system, I am telling. Okay, because you will be feeding everything in the Cartesian coordinate system only. Natural coordinate, that package will take care. Okay, at node 3, we are calling it as x3, y3. Okay, geometry, these coordinates of node 3 with respect to the reference axis x and y. Right, now you take any interior node whose displacement is uv. Okay, the technical component of displacement is uv. Its coordinate is xy. Now, if I write u1 equal to the shape function relates it, okay, n1 x1 plus, first u1 is equal to n1, u equal to, u is equal to n1 u1 plus n2 u2 plus n3 u3. Similarly, v is equal to n1 v1 plus n2 v2 plus n3 v3. Okay, so this shape function is used to relate the variational displacement within the element. That is displacement. Displacement in the element is obtained from the shape function n1, n2, n3. Similarly, if you want to obtain the coordinate, that is geometry, nothing but geometry, xy of that point, no, x is equal to n1 x1 plus n2 x3 plus n3 x3. X is equal to n1 x1 plus n2 x2 plus n3 x3. We can write. Similarly, y is equal to, if you want to obtain y, n1 y1 plus n2 y2 plus n3 y3. Okay, so the same shape function is used to obtain or represent the variation of displacement as well as that is in simply displacement. The same shape function is used to obtain displacement and geometry of the element. Okay, hope you would have got it. The same shape function, if the same shape function is used to obtain the displacement is what? Just now I told uv inside at any point in the element, right? And the geometry means coordinates xy of that interior point, right, is used. We call it as isoparametric elements. Those elements are called isoparametric elements. The best example is your triangular element. Your three-noded triangular element is the best example for to represent the isoparametric elements. Okay, they are called isoparametric elements. Sometimes what will happen, you will be using higher degree of shape function to represent geometry when compared to lower degree of shape function to represent displacement. Okay, sometimes higher degree of if you use lower degree of shape functions to represent in other words, same degree of shape function is used in isoparametric element, but in subparametric element we use less degree of shape function to represent geometry, but a higher degree of polynomial shape function to represent displacement. That is called subparametric element. In superparametric element, let us see. We will have whether I am telling correctly or not. I have to see it. Okay, let us see. In many engineering applications, the use of isoparametric elements has become common. That's what it's very commonly used, isoparametric elements, and this facilitates easy discretization. Some teacher may think discussing all this properties of element is a waste of time. Straight away they will go to application of this one, how to develop element stiffness matrix and how to analyze a structure by finite element procedure. Straight away people teach only concentrate or that, like your matrix method of structural analysis, straight away going for analysis of this one without discussing the basic fundamentals involved. But I want to give, because you should know what is the finite element method. That is important. Okay, in many engineering applications, the use of isoparametric elements has become common, and this facilitates easy discretization of the structure. Okay, why? The structure can be easily discretized if you use only triangular element, rectangular element, quadrilateral element, easily it can be discretized. That is why these isoparametric elements are most widely used, right? Isoparametric element is one in which the displacement and geometry, just now I told you, the displacement geometry variation, okay, it is a variation of displacement, variation of geometry, okay, that is coordinates and a field variable, right? Field variable inside. Okay, the isoparametric element is one in which the displacement and geometry variation are both described by the same shape function. Shape function, another name is there, no? Hope you may be remembering, interpolation function. Okay, for both described by the same shape or interpolation function. That is, the degree of interpolation function to describe both geometry and displacement is same. The n1, n2 are the same shape function we are using. The degree of shape function will be the same. Okay, the degree of interpolation function, that is shape function, to describe both geometry and displacement is same. That is the meaning of it. Okay, so isoparametric element is one in which the displacement and geometry variation, right, are both described by the same shape or interpolation function. That is, the degree of interpolation function to describe both geometry and displacement is same. Okay, while subparametric elements are having lower degree of interpolation function to describe geometry. Please see here, subparametric element, when you use lower degree of interpolation function to describe geometry, compared higher degree function for displacements. Okay, geometry, if you use lower degree of shape function, while higher degree of shape function for represent displacement variation, if you use it, we call it as subparametric element. The superparametric elements have their displacement described by lower order and their geometry being described by higher order interpolation function. That's what. If higher order interpolation function is used to represent geometry, we call it a superparametric element. If the same degrees of shape function or interpolation function is used to represent the displacement and geometrical variation, we call it as isoparametric element. Okay. If higher order degree of shape function is used to represent geometry variation and lower, okay, what did I say? If lower degree of shape function is used to represent geometry variation and higher degree of shape function is used to represent displacement variation, it is called subparametric element. Okay. If higher order of higher degree of shape function is used to represent geometrical variation and lower degree of shape function is used to represent displacement variation, it is called a superparametric element. Okay, that's all. This way you remember. You can write it in your own sentences, no problem. Any manner you can write it. Read it, understand, and try to write anywhere you are asked, because frequently the question paper I have seen explain isoparametric element, define isoparametric element, explain subparametric element, superparametric element. These are the questions in many Anna University question paper and many wherever finite element method, sign unit properties of elements. These questions will appear. Okay, you will be asked to explain what is isoparametric element, what is subparametric element, what is superparametric element, and all. It's okay. That's what example I have given here. Isoparametric element, two-noded axial element is a isoparametric element. Three-noded triangular element is a best example for isoparametric element. Both are okay. And then four-noded quadrilateral element or rectangular element also best example for isoparametric element. Eight-noded hexahedral element, four-noded tetrahedral elements. Okay, this discussion and all taken from C.S. Krishnamurthy textbook. Okay, all these things, all this discussion, the notes of isoparametric element I prepared from C.S. Krishnamurthy book. You can see all these examples also. Similarly, subparametric element. Okay, subparametric element, beam element. Beam element comes under subparametric element. Remember, best example, plate bending element, 6-noded triangular element, 10-noded tetrahedral element, and 20-noded hexahedral element. Okay, remember few elements to quote examples. Okay, try to memorize. At the student level, you have to, because when I was a student, I memorized so many things. My memory power was also very good that time. Now it has become very poor now. It's okay. Subparametric elements, right? So superparametric elements. The example for superparametric elements is three-noded cantilever edge triangular element. Three-noded, sorry, curvilinear. Three-noded curvilinear edge triangular element, right? And then four-noded curvilinear edged quadrilateral element, etc. Even that linear elements, there is a curvilinear edged elements are also there. There are so many, right? Because it's a vast area. This okay. Isoparametric elements necessitate the use of natural coordinates, and it is convenient to express the variation of geometry displacement by the same parameter. As per the definition of isoparametric elements, I have written here. I already told you, no, you take for a plane element, you take a plane element. Okay. For example, U is equal to Ni Ui means what? N1 U1 plus N2 U2 plus N3 U3 like that. V is equal to sigma Ni Vi means what? N1 V1 plus N2 V2 plus N3 V3. That's what written here. Similarly, X is equal to sigma Ni Xi. It means what? N1 X1 plus N2 X2 plus N3 X3. Y is equal to sigma Ni Yi means N1 Y1 plus N2 Y2 plus N3 Y3 for plane element. For example, for a triangular element, I told you. Okay. And then if it is happen to be a solid, in addition to UV, W also there. Okay, W. If it is a three-dimensional for solid element, in addition to XY direction, you have Z direction. No, so the displacement along Z direction is W. Okay, Ni Ui, sigma Ni Ui V equal to sigma Ni Vi, and W equal to sigma Ni Vi, Wi. Okay. Similarly, X equal to sigma Ni Xi, Y equal to sigma Ni Yi, and Z equal to sigma Ni Zi. I hope you will understand what it means for solid element, for plane element. Okay. Now, isoparametric element, this is the condition. Okay. Also, Ni equal to for a forward, some discussion is there, not necessary. Okay. What is that written here? Right. The formulation of a plane, okay. The formulation for a plane isoparametric element is described in the following. The same may be extended to solid isoparametric element also. When the real element is in quadrilateral, okay, please listen here. When the real element is a quadrilateral in XY system, the same element becomes a master or parent element in natural coordinate system RS. That's what. This discussion I don't want to discuss in detail. I don't want to explain. Just remember, read it as it is, because the same manner it is given in C.S. Krishnamurti book without much explanation. See here, we have this quadrilateral element whose non-degrees of freedom Q1, Q2. Instead of V1, U1, it is written here Q1, Q2, Q3, okay, Q3, non-degrees of freedom Q1, Q2, Q3, Q4, Q5, Q6, okay, Q7, Q8, like that it is represented. That's why you used the term Q instead of U1, V1 and all. It's okay. Anything, any notation you can use to represent the nodal degrees of freedom. And its coordinates x1, y1, Cartesian coordinates. Okay, x, y, somewhere is the reference axis. x1, y1, x2, y2, x3, y3, and interior point also P. Okay, y is, it is supposed to be Q, and here he used UV. Here he used UV to represent the nodal degrees of freedom of interior node. Okay, P, its coordinate is x, y, something, it's called a four-noded quadrilateral in XY system. When you convert this into natural coordinate system, this quadrilateral element is converted into natural coordinate system. What happens? This became parent or a master element. In RS system. Okay, parent element, four-noded quadrilateral in RS system. It becomes like this. Okay, in a natural coordinate, because natural coordinate, minus 1, minus 1, 1, minus 1, like that. Okay, RS system. P also in the term of R and S. Okay, this becomes, you can put some arrow like this. Okay, it becomes like this. This discussion is required, something. With this, I am going to finish this unit, properties of elements. Okay, since two coordinate systems are involved in the transformation, it's a transformation. Since two coordinate systems are involved in the transformation from real element to parent element or master element, a connectivity between XY system and RS system has to be established, which is possible through a Jacobian matrix. Since R and S each is a function of X and Y. Since R and S each is a function of X and Y, we use Jacobian matrix to connectivity between XY system and RS system. We use a matrix called Jacobian matrix. Sometimes you will be asked to some question paper I have seen. What is Jacobian matrix? Explain Jacobian matrix. Na? It is a matrix used to connectivity between SY system and RS system in order to convert while transformation. Okay, the transformation of real quadrilateral element to parent or master element in RS system, natural coordinate system. Something you have to write. What you understand here, that you have to write. With this discussion, this much discussion is there in the textbook also. That is why I have written this much. Okay, but in certain book I have seen with the Jacobian matrix, and we will not go too much into detail, because already whatever we have discussed is itself too much for you. Okay, so that's why with this signed unit is over. I wind up signed unit. Okay, properties of elements. I wind up here, right? The signed unit is over. Next class I will be starting third unit. Okay, I have to go through your syllabus. It's okay. I will go through, because you can, if you want, we can say mesh generation techniques. We can discuss about it, and then properties of. Okay, next I will teach you formulation of element stiffness matrix. Okay, next class onwards. First, let me to record your names, right? This much discussion is more than sufficient for today. Very good. Always, I didn't expect. Okay, M.Tech students are very sincere students. Very good. I'm so happy to see. First hour you are attending, all full attendance is there. It's really good, right? So I'm happy to see you all, right? All of you are attending. Very nice. Good. Okay. So I have recorded your name, right? Good. I will stop recording. Then I want to have a discussion with you. Wait for some time. Okay. Bye to all of you. Bye.